Section 7.2, areas in the plane. 2 more sections left. Quick review quiz. Find the area between the x-axis and the graph of the given function over the given interval. Be careful, it says find the area. So that does mean find total area between the x-axis and the graph, not net area. And then number 2 says find the x and y coordinates of all points where the graphs of the given functions intersect. You may use your calculator for all of those points, and that will be a 6-point quiz when you come in tomorrow. I want to go through and explain the concept to you, and then I'm going to have a couple examples that somebody else is going to explain to you. Not our friend with the bow tie, but someone other than that. So, first concept is, how can we find the area between these two curves? And I have here the parabola, y equals 2 minus x squared, and then I have this graph negative x. And I would like to try and find the area between these two curves. We could split the area into several sections and use subtraction and figure it out. Like, we could integrate from here to here, and then from there to there, and then from here to here down below, and add and subtract all these different pieces. But there is actually a very easy way to find the area between two curves. Consider a very thin vertical strip that I have put into these two functions together. We should hopefully agree that the length of this strip would be the top function minus the bottom function. So if I put 1 into my function, I would put 1 into my top to get the length from above, from this top point to the x-axis, and then I would put 1 into my negative x to get that length, and if I subtract the two of those values, I would get the length of my strip. So we have 2 minus x squared minus negative x. Since the width of my strip is a very small change in x, we're going to denote that as dx. So I have y1 minus y2 times dx. So when I take my length times my width, I will get 2 minus x squared plus x, that's the length of my strip, times dx, that very thin little width of that rectangle I put in there. If we add up all those strips, we are technically integrating. So we are going to take the integral of the function 2 minus x squared plus x dx over the interval negative 1 to 2. And there you have it, folks. That's the concept. My antiderivative is 2x minus 1/3 x to the third plus 1/2 x squared. I will then put 2 in and then subtract what I get when I put negative 1 in. So I have 27/6, which reduces to 9/2, which is about 4.5. So here is the formula to find the area between two curves. It's just the integral from a to b of the top curve minus the bottom curve, dx. We use it so much, you really don't even need to worry about memorizing it, because you're going to start to it's going to become second nature here. I have a couple examples. This first example, well, I actually just have this one example, but we have the square root of x, and then we have x minus 2, but I only want to find the area above the x-axis, so I've cut it off by the x-axis, or at the x-axis. If we put in vertical strips, we do have to integrate it in two parts, and here's why. This x minus 2 does not actually just stop, it actually continues on down below. So if I integrate from 0 all the way to 2, I'm actually, of my top minus my bottom, I'm actually taking this area in this piece as well as this area down below, and I don't want that. I just want it to be bounded by the x-axis. So I can't really integrate from 0 to 4 of the top minus the bottom, because I need to find a way to cut this out. So if we were doing vertical strips, what we would do is we would just take the integral from 0 to 2, where this x minus 2 crossed the x-axis, of just my top, because that would be the area under the curve to the x-axis, and then add it to my area from 2 to 4 of the top minus the bottom. But now we have that integral set up, 0 to 2 of the square root of x dx plus 2 to 4 of the square root of x minus 2 dx. But we could actually put in horizontal strips, and now this thin little width of my rectangle is dy rather than dx. And so what I then could do, since the width of the strip is dy, we can find the length of the strip by solving for x in terms of y. So y equaling the square root of x is also the same as y squared equaling x, if I just solve it for x. And y equaling x minus 2 is the same as y plus 2 equaling x. So I can change everything around and integrate from 0 to 2 of my top. If I would turn it, this would be on the top minus my bottom. So that's why it's y plus 2 minus y squared dy. So when I find my antiderivative, I have 1/2 y squared plus 2y minus 1/3 y to the third. I'll then put 2 in and 0, which is 10/3. General strategy for the area between curves. You need to sketch the curves for sure to make sure you know which one is above and which one is below. You need to decide on vertical or horizontal strips. Pick whichever is easier to write formulas for, and whichever also will let you integrate fewer times. There's not really a set rule that you have to use dy in this situation or dx in another situation. Sometimes one is just easier than the other one. Write an expression for the area of the strip. If you're integrating with respect to x, your length has to be in terms of x. If you're integrating with respect to y, your length has to be in terms of y. And then number 4, find the limits of integration. If you're using dx, your limits are going to be x values. If you're using dy, your limits are going to be y values. And then we will integrate it to find the area. So that is it. That's the general concept. I'm going to put a few more examples in of how to do some different problems. And then when you come in on Monday, we will talk a little bit more about this concept. Have a good weekend, and we'll talk to you all later.
Find the area of the region bounded by the graphs of y equals x squared and y equals x plus 2. Here's a picture showing the two graphs and the region whose area we'd like to compute. The first thing we want to do is find the x-coordinates of the points of intersection of the two graphs. Those will end up being our limits of integration. So what we'll do is we'll set the two functions equal to each other and solve for x. We rearrange the equation and factor, and we find that the two roots of the equation are x equals minus 1 and x equals 2. Now let's look at a typical vertical slice in the region. The top of that slice is along the straight line y equals x plus 2, and the bottom of the slice is along the parabola y equals x squared. So the length of that slice is x plus 2 minus x squared. So we'll write our area differential dA as x plus 2 minus x squared times dx. And so the area is the integral from x equals minus 1 to x equals 2 of dA. Now we'll antidifferentiate each term. We get 1/2 x squared plus 2x minus 1/3 x cubed, and we evaluate that between minus 1 and 2. The value at 2 is 2 plus 4 minus 8/3. The value at minus 1 is 1/2 minus 2 plus 1/3. Now let's do this arithmetic by first gathering together all the whole numbers. We have 2 plus 4 and then a minus minus 2 for an 8. Then we have minus 8/3 minus another 1/3, which is minus 9/3, and then we have minus 1/2. Of course, this is 8 minus 3 minus 1/2, or 5 minus 1/2, which is 9/2. Example. Find the area of the region bounded by the graphs of y equals 2 times the square root of x, y equals 0, and y equals 3 times the square root of x minus 5. Here's the graph of y equals 2 times the square root of x. The graph of y equals 3 times the square root of x minus 5 touches the x-axis at x equal to 5. It looks like that. The graph of y equals 0 is the x-axis, so the region that we're interested in is shaded here in yellow. The first thing we'll do is find the point of intersection, which will help in determining our limits of integration. To do that, we'll set 2 times the square root of x equal to 3 times the square root of x minus 5. Next, we square both sides of that equation, and then by subtracting 4x from both sides and adding 45 to both sides, we arrive at 45 equals 5x. And so x equals 9 at our point of intersection. For the y-coordinate there, we could go back to either of the two functions. The simpler of the two is 2 times the square root of x, so we have 2 times the square root of 9, or 6, for the y-coordinate. Now let's look at vertical slices here. Toward the left side of the region, a vertical slice touches the graph of y equals 2 times the square root of x and y equals 0. But if we move to the right, the slice then touches y equals square root of x and y equals 3 times the square root of x minus 5. So if we follow this approach, we're going to have to break the region up into two pieces, because the length of the slices will need to be described differently in different parts of the region. The cutoff point here is at x equals 5, clearly. And so to get the area of the left part of the region, we'll integrate from 0 to 5, 2 minus the square root of x minus 0. And to get the area of the right part of the region, we'll integrate from 5 to 9, the y-coordinate on the top curve, which is 2 times the square root of x, minus the y-coordinate on the bottom curve, which is 3 times the square root of x minus 5. Now these are not difficult integrals to do, but there's a simpler approach here that will allow us to capture the entire area with one integral. The key here is to look at a horizontal slice located at a height of y. This is because the length of that slice can be given by a formula that's independent of where it is in the region. In other words, all horizontal slices are basically the same. The length of the slice is going to be given by the x-coordinate on the right end minus the x-coordinate on the left end, but these have to be described in terms of y. So we need to solve for x in each of those two equations involving square roots. For the curve on the right, we'll divide by 3 and square both sides, and then add 5 to obtain x equals 1/9 y squared plus 5. For the y equals 2 times the square root of x curve, we'll square both sides and divide by 4, and write that as x equals 1/4 y squared. So our slice area is going to be given by the x-coordinate on the right, 1/9 y squared plus 5, minus 1/4 y squared, and then times dy. Now let's simplify that a bit. 1/9 minus 1/4 ends up being 5/36. Let's also go ahead and factor out 5/36 so that we have 5/36 times 36 minus y squared dy. Now, y-coordinates in our region extend from y equals 0 to y equals 6, so that's the interval over which we want to integrate dA. So the area is the integral from 0 to 6 of 5/36 of 36 minus y squared dy. This is a fairly simple calculation now. Our antiderivative for 36 minus y squared is 36y minus 1/3 y cubed. And we evaluate that between 0 and 6, which is 536 times 216, minus 1/3 of 216. So we have 536 times 2/3 of 216, which is 144, and 144 divided by 36 is equal to 4, so our area ends up being exactly 20 square units. Example: find the area of the region bounded by the graphs of y equals x squared and y equals x to the fifth two ways. By that we mean by integrating with respect to x and by integrating with respect to y. Here's the parabola y equals x squared. And here's the graph of y equals x to the fifth. Notice the points of intersection are obviously the origin as well as the point 1, 1. And here's our region. Now let's zoom in on that a little bit. Let's first look at vertical slices. This corresponds to integration with respect to x. Here's a vertical slice located at an arbitrary x. The top of that slice is on the curve y equals x squared. The bottom is on the curve y equals x to the fifth. So the length of the height of that slice is going to be x squared minus x to the fifth. And so our dA is x squared minus x to the fifth times dx. So the area is the integral from 0 to 1 of that dA. The computation here is easy. The antiderivative we want is 1/3 x cubed minus 1/6 x to the sixth. And evaluating that between 0 and 1 gives us 1/3 minus 1/6 or 1/6. Now let's do the computation from the point of view of horizontal slices. That will correspond to integration with respect to y. So suppose we have a horizontal slice located at y. Its length is going to be the x-coordinate on the right minus the x-coordinate on the left, but those have to be described in terms of y, so we solve y equals x to the fifth for x, getting x equals the fifth root of y, and solve y equals x squared for x, getting x equals the square root of y. So dA here is going to be y to the 1/5 power minus y to the 1/2 power times dy, and the area is the integral from 0 to 1. Notice that's y equals 0 to y equals 1 of y to the 1/5 minus y to the 1/2 times dy. Now again, this is a straightforward calculation. Your antiderivative here is 5/6 y to the 6/5 minus 2/3 y to the 3/2. And we evaluate between 0 and 1, obtaining 5/6 minus 2/3, which is equal to 1/6. One more example. Let's find the area of the region bounded by the graphs of y equals 3 times 1 minus x squared and y equals 4 times the square of 1 minus x squared. Now let's get a picture of what we're dealing with here. Here's the parabola y equals 3 times 1 minus x squared. Notice the x-intercepts are plus and minus 1, and the maximum value of 3 occurs at x equals 0. In the other equation, y is equal to a fourth degree polynomial in x, with zeros at plus and minus 1, and a value of 4 at x equals 0. It turns out that the graph looks like this, and so the region bounded by the two graphs looks like so. Now notice that there are 4 points of intersection, 2 of which are obviously located at plus and minus 1. The other 2 are indicated here, and to find those, let's set our two functions equal to each other and solve. Since we're looking for solutions other than plus and minus 1, we may as well divide through by 1 minus x squared here to obtain 3 equals 4 times 1 minus x squared. Now we multiply out the right side, do some rearranging, and we have 4 times x squared equals 1. So x ends up being plus and minus 1/2 at each of those points of intersection. Now notice that we have symmetry here about the y-axis, which tells us that we may as well just compute half the area and then multiply by 2 later. Now since the curves cross at x equals 1/2, we're going to need to break the calculation up into 2 parts. We'll calculate one integral from 0 to 1/2, and then another integral from 1/2 to 1. Between 0 and 1/2, the top edge of the region is the fourth degree curve, and the bottom edge of the region is our downward opening parabola, so the length of a vertical slice there is given by 4 times the square of 1 minus x squared minus 3 times 1 minus x squared. Between 1/2 and 1, it's just the opposite, so we'll integrate from 1/2 to 1, the opposite difference. Now let's work out these integrals. We'll first simplify the integrands. Notice that each one is just the negative of the other. Now when we multiply out 1 minus x squared squared, we pick up an x to the 4th term, so we have a 4 times x to the 4th, and we also get a minus 2x squared, which gets multiplied by 4 for a minus 8x squared, and then we have a plus 3x squared from the other term, so we have minus 5x squared, and the constant term ends up being 4 times 1 minus 3 times 1 for a 1. So we'll integrate from 0 to 1/2, 4x to the 4th minus 5x squared plus 1, and then integrate from 1/2 to 1 the negative of that function. Now let's antidifferentiate and evaluate between the endpoints. Our antiderivative is 4/5 x to the 5th minus 5/3 x cubed plus x, and for the second term we just have the negative of that same antiderivative evaluated between 1/2 and 1. Now we substitute 1/2 into the first term and subtract its value at 0, which is 0. Then we add the value of the second antiderivative at 1 minus its value at 1/2, and so now let's do all this arithmetic, or exactly 1/2. Now remember, that's just 1/2 of the area, so we'll multiply by 2 to get an area of exactly 1.